Hey everyone, we are making a little video here to help with related rates portion of stats and calc project. In this case, I've just invented a scenario to let you see how you can put your data into action with a related rates type of interpretation. Okay, so in this scenario, I've got a sailing boat that is subject to a changing wind speed. I'm measuring wind speed in meters per second and the sailboat in knots just to vary it a little bit and have the numbers not be really similar. In this case, it's over a decimal hour or slightly less than an hour, starting at 1.1 going up to 1.8. You could do this in minutes or whatever scale you wanted. All of these things, the scales are somewhat arbitrary, but the relationship is, guess what, pretty determined. As you have an increase in the wind speed, you can expect an increase in the boat speed or vice versa. All right, so what I did was I took the data over time, and I've got two different graphs that represent, in this case, the wind speed over time or the boat speed over time. And so if we go into Desmos, this is a graph of the boat speed in red, slower than the wind speed there in blue. So as one goes up, so does the other. As one goes down, so does the other. So to model those curves, I just you can go down to this menu and pull down and try different things. In this case, if I said, let's see if it's close to a quadratic regression, I would get that for the wind speed. And that's really pretty good. I could have used that just to be a little bit fancier. I went with a quadratic regression. And but when you get a curve that you think is good, you can click on this icon here and it will produce that equation that you can then edit. You can make it into a function and you can find a derivative easily that way. This is what I did with the fourth degree polynomial regression, and I also just deleted some of the many decimal places just so I could see what was going on and cleaned it up a little bit. So here are my two regressions. I'll turn this one off. And again, they're not perfect. I'm just illustrating the idea here. So there is that. And I can then find the derivative. So here's the derivative of the wind speed. Now that's going way off the scale. If I'm producing this for a poster, I could easily multiply this by 0.01 and that would scale it down, but I would just need to say, derivative scaled down by a factor of 10 or at 10% or something like that. Here's the other derivative for the wind speed, not going off the charts crazy, but just to be consistent, if I made that also scale down, there it is. Okay, so there are the derivatives. I'm going to eliminate those for now, though, because you'll see we're going to use that later. Now, in terms of the related rates, if I'm going to compare the wind speed to the boat speed, I need a separate graph. So going back to this is where I've got the wind speed versus the boat speed, that data right there. And I did a separate Desmos graph because if I put it in my first one, it just squashes the scale way down and makes it very difficult to read. So a separate graph is required in this case. Maybe not all the cases, but very commonly, yes. Okay, so there's my data. It looks like, guess what, as the wind speed goes up, so does the boat speed. But you can imagine that there's kind of a law of diminishing returns, that the wind can keep getting stronger and stronger, but the boat speed just can't go beyond a certain speed. It's just, you're not going to, for every time you double the wind speed, double the boat speed. Doesn't work that way. So here's a logarithmic model right there. That's a logarithmic model, and that's not too bad. And then here is the square root model, okay, and that's also not too bad. So you would sort of sensibly choose between one or the other. This one looks like it might fit the data better. However, if you think about the physics of it, perhaps you could say that there's some sort of law in physics that might make the logarithmic model a little bit better. Anyway, I did both just by comparison. So if you see both of these functions right there, both of them, you can find the derivative of with respect to time, and that's how we do our related rates. So if I go to a worksheet here that I've typed out, again, here's our scenario. How will the rate of change of the wind affect the rate of change in the boat speed? And this again there's not a lot of real science in this, but this shows you the technique that you could use to bring to the real science that's in your poster project. Okay, I just picked at point 1.7. I could have picked any data point. Essentially, this is one that I thought was more interesting because it was at a period of decline in the wind speed and the boat speed. So at that instant in time, if you go back to the original data, the wind speed happens to be 12 meters per second, and the corresponding boat speed at that time is 5.2 knots. Okay, so I don't know if I can turn that off. Yep. So that's like my snapshot data. All of this information here is like my snapshot data. Okay, so then to find the related rates, I go to my regression formula, and then I just take the derivative with respect to time, just like we've done in other related rates problems. The derivative of the ln of w is 1 over w. Multiplier is still there. Then don't forget to take the derivative of the inside with respect to time, and that's just my dw dt. So I go back to my snapshot data, and I fill in, that's supposed to be a w there. I fill in the wind speed, and that is 12 right there. I fill in the rate of change. How did I get that negative 72.7? If I go back to my graph to see where that comes from, go back to my graph. Okay, that's if I fill in, right here it was, you can see that when I fill in the derivative at 1.7, my rate of change there is negative 72.7. Okay, so that's where I got that number right there. When I crunch those numbers and type them in, I get negative 19.8. So I would predict that the rate of change of my boat speed based on the change in the wind speed would be that. All right, so here's another same thing, different regression function. Again, I take the derivative. This is where you get to show your derivation skills. It's going to be then 1 over 2 times the square root of that. And I plug in, again, my wind speed, and I do the math, and I crunch those numbers, and I get something that's similar. That's not exactly the same, but again, it represents that it would be as the rate of change of the wind is dropping by 72.7 per unit of time. This would be changing by negative 22.7. Okay, I can then compare this to what it really appears to be based on my regression function, going back to this, and that's what this value is right here. And we get, in this case, negative 25.23. So that, in a sense, is confirmation that we're in the ballpark. Why are these not perfectly in agreement? Because I was using a data point. I was not using a point on my regression functions. If I had just used the regression function, I would get much better agreement. But I'm using a data point, which is a little bit adrift from that regression function. Okay, so that's the basics of how to do that. Hopefully you can pause and re-listen. A few little things to note that some people weren't sure of. You can change the color and things like that by holding down the cursor over that, and you can change the color to orange. You could change the line to a different type of dotted line. You can change the line thickness here if you want to make them thicker. This could be like really thick. So you can have control over your display of these graphs. Okay, good luck everyone.